Section 6.3, Day 1, Vectors in the Plane.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah!
So what is a vector? A quantity that has both magnitude and direction, represented by a directed line segment. So in the example here, you see that the initial point is point P, and the terminal point is point Q. Now you don't see necessarily a point at the end of this, because it has to indicate the direction that it is going. But the magnitude is the length of that line segment, but it's a directed line segment, so there's an initial and a terminal point. It's denoted by the double vertical bars, and we're going to use the distance formula to calculate the magnitude. Equal vectors have the same magnitude and the same direction. So you can see vector V and vector W. So vector V is the directed line segment RS, and vector W is the directed line segment PQ. To be able to identify if these are equal vectors, we need to identify if they have the same magnitude. So we'll use the distance formula to show that they have the same length, and then the same direction, which has to do with your slope. So we'll do slope for direction, and then magnitude, we will be looking at the length. So we will start by looking at the magnitude. So the point of R is at -5, 3, and the ordered pair for S is at 1, 7. So to find the magnitude of vector V, that's equal to the square root, we're using the distance formula, the change of x squared plus the change of y squared. Doesn't matter the order that you subtract them, because you're going to end up squaring that number anyways. So -6 squared plus -4 squared, and that'll be equal to 36 plus 16, or the square root of 52, which can be simplified because the square root of 4 is a perfect square, so you can simplify that. And so that'll be 2 square roots of 13. So therefore the magnitude of vector V is 2 square roots of 13. Now let's go ahead and look at vector W. So point P is at 0, 0, and point Q is at 6, 4. So we will find the magnitude of vector W. And so we'll do the change of x. 6 minus 0 squared plus the change of y, 4 minus 0 squared. And then that'll be the square root of 6 squared plus 4 squared. So once again, we get the square root of 36 plus 16, which is the square root of 52. So once again is equal to 2 square roots of 13. So we know that vector W has a magnitude of 2 square roots of 13. Now we'll look at the slope, so we can see if the directions are the same. So the slope of vector RS, we will do the change of y, 7 minus 3, divided by the change of x, 1 minus -5, so it'll be 1 plus 5. 4, 6 reduces to 2/3. So the slope is 2/3 for vector V, and then for vector W. So we'll be looking at the slope for the directed line same at PQ, which is vector W. This will be the change of y again, so it'll be 4 minus 0 divided by the change of x, 4 6, which reduces to 2/3. So therefore we know that vector v is equal to vector w. So vector v is equivalent to vector w, which means they have the same magnitude and the same direction. The next thing we're going to look at is a vector in standard position. A vector in standard position has its initial point at the origin, so it's 0, 0, and it can be represented by its terminal point, v sub 1, v sub 2. So if you look at the last slide, we had vector w in standard position where its initial point was at the origin, and so we could represent that vector using its terminal point, 6, 4. Component form of a vector is a vector that is not in standard position, so its initial point is not at the origin. So the one on this one, that would be vector v. So let's take a look at that. So vector v was at the point negative 5, 3, 1, 7. So about right here, negative 5, 3, and then 1, 7. So that was not in standard position. So the component form of this vector, how you find that is you're going to subtract q sub 1 minus p sub 1. So you're going to take your terminal point, x-coordinate, minus the initial point's x-coordinate. And then you're going to take q sub 2 minus p sub 2. And then that will give you vector v in that component form. So what this would look like on our previous vector v is we would take the 1 and subtract negative 5, and then we'd have 7 minus 3, and so that would give us 6, 4. And so you can see that I'm writing this with these pointed brackets called angle brackets. This is what we use to write vectors. So this one up here in standard position would have also been the terminal point that we said was 6, 4. So because they were equal vectors, they should have the same when we write it in component form of the vector when we subtract. Remember, when doing component form of a vector, you have to take the terminal point minus the initial point. So it's the terminal point minus the initial point. If you do it the other way, then it's going to have the wrong direction. The magnitude of vector v in component form is you subtract your x-coordinates, your q sub 1 minus p sub 1 and square it, plus q sub 2 minus p sub 2 and square it, and then take the square root. So that's your v sub 1 squared plus your v sub 2 squared, and then the square root of that, still using the distance formula. A zero vector is denoted by 0, 0. Zero vector has no magnitude, so you're not going to see anything but just that point at the origin. So you can see that the magnitude is equal to 0. A unit vector is when you have one unit, so the magnitude is equal to 1 for a unit vector. Okay, let's take a look at example 1 here. Find the component form and the magnitude of vector v with its initial point at negative 2, 4 and terminal point at 4, negative 4. So vector v with an initial point at negative 2, 4 and terminal point 4, negative 4. We need to subtract, but remember, terminal point minus initial point. So 4 minus negative 2, and then negative 4 minus 4. And then you just simplify. So 4 minus negative 2 is 6, negative 4 minus 4 is negative 8. So the vector v is equal to 6, negative 8. Now to find its magnitude, we're going to use the distance formula. So we've already done the subtraction when we've done the 4 minus negative 2. So now we just need to take 6 squared plus negative 8 squared. That'll be 36 plus 64. So the square root of 100 is 10. So the magnitude of vector v is equal to 10. So if you look at this on a graph, your vector is at 6, negative 8, so 6 in this direction, negative 8 here, with a magnitude of 10. So its initial point is at 0, 0. We have the direction, and then we have the length, which is 10. So that's what it would look like on a coordinate plane. Alright, the next thing is vector addition. So given vector v and vector w, we're going to graphically show the addition of the vectors. So sketch a graph of each expression, v plus w. And we're only sketching these, so we're not going to be measuring and everything. We're just going to kind of eyeball it. So on part A, v plus w, so we have vector v. Okay, and we're going to add vector w. So once you have vector v, you're going to add w. So from the initial to the terminal, and then the terminal of v now becomes the initial of w, and you just kind of add it on there. Now the final result is what we want. We want to know what v plus w is. Right now we just have v and w added together. So the final end result is v plus w. So you start with your initial point of v and end at your terminal point of w. So we're going to draw from the initial to the terminal. Make sure you get that arrow in, because what we're looking for is what v plus w is, and make sure you indicate that. So the end result is the black line segment, or directed line segment, v plus w. So that's what your answer is. That's what v plus w represents. This is called the resultant vector. Alright, let's look at b, vector w plus vector v. So we'll start with the w this time. And so w is about right there. Plus v. So now we'll start at the terminal point of w and draw in vector v. So the resultant vector is from the initial point of w, vector w, to the terminal point of vector v. And this would be vector w plus vector v. If we compare A and B, does v plus w and w plus v look to be the same magnitude and direction? They look like they are equal vectors, and they are. You can add vectors in different orders and get the same resultant vector. And then we have C. C is v minus w. So we could rewrite this as v plus negative w. So v, once again, we'll start there, and then we want to add negative w. Remember, negative w is the opposite direction, so it's still going to have the same magnitude, but we're going to go in the opposite direction. So instead of going up like this, we'll go down and to the left. So down and to the left. And that represents negative w. So the resultant vector is from the initial point of v to the terminal point of, in this case, the opposite of w. So v minus w is our resultant vector. And remember, negative w is in the opposite direction. Same magnitude, but opposite direction. Alright, and the last operation we're going to look at is called scalar multiplication. Scalar multiplication is a number that has only magnitude. So only magnitude. If the scalar is negative, the vector has opposite direction from what we just talked about on the last slide. So scalar, once again, only has to do with the magnitude of the vector. So in example 3 here, we're going to take the vector v, and we're going to multiply it by the scalar of 2. So you have vector v, and then you have another vector v. So there's 2 of them. And so the resultant vector doesn't change in terms of the direction. You still have your initial, but now your final, or your terminal, is all the way at the end. So that black directed line segment is 2v. Now on B, it's negative 1/2 v. So remember, the negative is the opposite direction, and we're also going to take half of the magnitude. So with vector v going up and to the right, we'll now go down and to the left. But remember, we also want half of that as well. So we'll go down and to the left, but only half of that, and that would represent negative 1/2 v. So you still have your initial and your terminal, but it's half of the original. So the last slide here is just your properties of vector addition and scalar multiplication that we've talked about today. U, V, and W will be vectors. C and D will be scalars. So we have the commutative property, associative property. That just means that you can add vectors in any order that you want, and you can associate, you can add two different vectors first and then add a third one later. So commutative and associative property work for vector addition. Your identity property, so if you take vector v and you add the 0 vector, then you just get back the original vector. Additive inverse, if you take a vector and add its opposite, then you get the 0 vector. If you take a vector times a scalar of 1, you're just left with the original vector. And if you take 0 times a vector, then the magnitude will be 0, so you'll get the 0 vector back. And then the scalars, just a couple different ones here. You can multiply two scalars together and then multiply it by the vector, or you can do it times the vector first and then do another scalar after that. When you're adding two scalars, you can kind of distribute that, so to speak. So it would be C times vector v plus D times vector v. And then if you're adding two vectors together, but a scalar is on the outside, same thing. You can take C times vector v plus C times vector w, or the scalar. And then the last one is, if you're trying to find the magnitude of a scalar times a vector, you can actually just find the magnitude of the vector and then multiply that by the absolute value of the scalar. And that's just because if the scalar is a negative direction, remember the magnitude is a distance, so it won't be a negative as well. So you just do the absolute value of that scalar times the magnitude of the vector. And lastly, once again, a lot of different things we've talked about in terms of vectors today. So make sure you go through, write those important things down, what the vocabulary means, what are all the different things we've talked about in terms of what a vector is, its magnitude, its direction, what component form is compared to standard position. So just a lot of different things that are going on today. So make sure you kind of summarize that all together and get all that information written down.